Okay, we have an easy problem today, and it is about majority number. So we're given list of numbers, and the half of the list is the same number, and all others are unique. So this is a half of the list. They're the same. All others are unique. And we asked to find this number. My solution is just to use hash map and frequency counter and just count each number. And then brute forcefully just find. So the easy problem requires easy solution. This is how it works, and I spent 8 times to just fight the Kotlin syntax, and the problem itself is kind of trivial, but it has hard solutions. Or medium, I don't know. And one of these is the majority vote. So if we have this kind of sequence or numbers, and some of them are majority, then there is a Boyer's Moore algorithm that can detect it, and it has the properties that majority should be bigger than half. But in our case, we have majority is exactly half, so we can't just simply apply Moore algorithm for the given array. And the trick is to skip one element first, skip and take the rest, and this would give us possibility to apply this Boyer-Moore algorithm, like this. And let's look how it works. We count have a frequency or baseline, initially 0. We skipping this first number, and we only counting these ones, and we are checking if each number is equal to the baseline, and if it's equal, we doing f++, or if it's not, f minus. So this is works, and the first gives us the baseline is 2 and frequency is 1. The second number gives us frequency 0, and when frequency is 0, we change in baseline, and baseline is the answer. This gives us frequency 2, and when frequency is 2, we already can return answer, because the property is that all other numbers are unique, and if we have any non-unique, then we find the answer. So this is how it works, and let's look at the code. I explored it. Let's look at my Rust solution. Okay, now let's look at the Kotlin solution first, and I do this kind of check of the first numbers, first position, because first can be actually the answer. We can just skip it. And then I decided to optimize it. Then look at this, like check. It's unnecessary because we use it in this check, so we can just remove it. We removed it. Yes. So this is how it looks like. However, it can be further optimized. For example, when we check in this with 0 position, we can check it here actually, because we're iterating over every other number. We can just check it here, and this would give us the result. Oh, this is kind of another tricky solution. I just it's not from me, it's just from the other guy. It's clever. But now let's return to the optimization of Moore algorithm. So I put this check inside the if, and it just works. However, it can be further optimized. As we see, we can just skip entire, and this is not my idea, it's idea from the other guy too, but this is the same idea. It's clever. So this is a most optimal and shortest solution I see. We compare the previous and with the 0 position, and otherwise we should return the last index. This is clever. So the sum solution is also kind of clever, because what is a sum? Imagine we have numbers like 1, 2, 3, 3, 3, 4, and the sum is the sum of this part plus this part, and this is a sum. Unique plus sum duplicate. And when we doing this to set, we removing the duplicates, like minus this one and this one, but we still keep this one. And this is kind of some hash set. And when we doing this operation of sum minus some hash set, we haven't exactly this sum result, but we should divide it by the count and this count is not the half, it's half with -1 because of this element. So this is the entire solution. It's also kind of short, and I would to keep it as to screenshot. So this is how it looks like. That's all for today.